First of all, thank you so much for the introduction. It's been really a pleasure to be invited again to be part of the series. But this lecture in particular, I would like to dedicate it to Mr. Leslie Robertson, who was deeply involved in the design development of the structural concept and design of this project with Sotin as part of LERA and in collaboration with Arab. Again, his legacy continue as we speak, and may his soul rest in peace. This lecture, I'm doing this lecture on behalf of Samsung CNT and UEM Construction. Again, and also like to thank PMP for giving us the opportunity to build this project. Without their full support, we probably would not have been able to do what we were able to deliver. Again, as Carl mentioned, early this year, we were able to talk a project about Lakhdar Center on the Northern Hemisphere with the complexity similar to this project. Maybe it's even more complex working in Russia. And now we're moving to the Southern Hemisphere, working on Merdeka 118. These two projects essentially started at almost the same time, but Lakhdar was not as big as this one. Now again, the project was probably, I would say, probably one of the most eventful projects that I've ever worked with in many different ways. Many technical challenges that we faced during the construction and during the optimization process. And also this project in particular is very large and very close to China town, which is this area being gentrified. And it's up and coming area. It's extremely busy. It was just really the overall traffic in that area was really very tough. So the overall logistic and the planning in terms of construction of this project was also another big challenge. And it's really the first time we have introduced ultra high performance concrete, which is up to 105 megapascal. Is not only the strength, but also for stiffness. So that we went through a lot of challenges in order to achieve that. And the last time, I think in Malaysia, the maximum concrete strength where they broke the limit on concrete was in the early 1990s when they built the Petronas Tower and achieved C80 concrete. Now we are using C105 and broke another record. But also at the same time, we have been hit by COVID-19, which caused a huge disruption to the overall operation and having to be able to complete the project on time. But regardless of all of that, we're able to complete this project in November this year, topping out. And now we're hoping to complete this project by the end of the year. Also, finally, I'd like to thank the Skyscraper Museum for continuing to try to invite us to these lecture series. So today I will be talking a little bit about some of the challenges that we face on this project, in particular to the construction and some of the issues that we dealt with. Again, as you know, this project had been initially was announced much shorter than this. At this completion of the pinnacle, it was announced to be at 678.9 meter tall, which made it the second tallest building in the world. And this is just the status of the project right now. And right now, Samsung has completed the second tallest building in the world from a construction standpoint. And this is just indicate, for example, in Malaysia has been breaking one record after another. After the Petronas Tower, we have the Merdeka 118, which is now the tallest. Now, Samsung in particular, as you see here, has built the tallest and the second tallest building in the world, and also participated in Taipei 101 and the tallest building in Europe, and which is Lakhdar Center. Now, the developer of this project is PNB, which is a National Capital Corporation, National Investment Corporation. And the employer was for this project in particular is PNB Merdeka Venture. And the contract administrator, external construction, the architect of the project, international architect, the FKA, out of Australia, and RSP is the local architect of record. LERA, which is led by Sotin and Leslie Robertson, have led the design internationally for civil and structural work. And Arab was a local architect, a local structural engineer on this project and an engineer of record. MEP is LER International, and KTA was local MEP. The contractor is Samsung in collaboration with UEM Construction. It was a joint venture for the entire development. Again, the project is mostly an office building from level 8 up to level 96 is an office building. From 97 to 118 is mostly a hotel and apartment suites. We have about 250 units and of that. Now, this site location, as some of you who are familiar with the KL, this is where the Petronas Tower and KL Tower are near each other. And Merdeka 118, essentially what they always called is the Golden Triangle. So by starting this project, this triangle has been formed. And as you can see here, the site location when we started this project is very, there was nothing in there. It's very close to Chinatown. It's very congested area. And at the same time, it's very close to very prominent historic sites, including the Merdeka Stadium, in which the independence of Malaysia took place, the ceremony, and also Negara Museum, Negara Stadium over here. And there's one small stadium near here. And also the infrastructure around the site is extremely complicated. But however, because of that, the client has made the major investment in order to improve the overall situation on the project, including traffic, including access, including many, many things. So they invested a huge amount to make the overall area much better. But at the same time, when designing this project, the architect and the client intention is to integrate everything together as one project and make integrated with the great assets that they have, especially related to the stadium. This project can be accessed through MRT, LRTs, and some of the express ways, and also there's a lot of improvement have been done by the client himself in order to make sure that the traffic and access is good. In terms of the project, it's also there was a lot of improvement to the cars. There's a lot of roads have been widened, or some of these have been access to the site to avoid congestions. There's a lot of traffic analysis have been done to make sure the site can accommodate this major development. Again, the project consists of the tower, which is about 118 story, 679. It's mostly an office building. And then we have the 3 tall residential towers, 2 on the west side that's go over the mall, which is a very large mall, both on the east side and the west side. And then we have 1 residential tower on the west side of the building. And as you can see, the promenade, which is also this green thing, in which the access is made accessible to the public, which make the access to the Merdeka Stadium and other things very inviting for people to have access to that. Now, the architectural design concept, as mentioned by Carol, is influenced by a mixture of diamond shape, faceted, derived from the traditional Malaysian songket pattern to signify diversity of Malaysia. But the spire itself, it's symbolic image that resembles the silhouette of the Prime Minister Tango Abdulrahman when he raised his hand chanting Merdeka, which means independence, to declare independence of the country at that stadium. Now, Samsung's scope of work in this particular project was absolutely huge. As you can see in the red box here, this is the entire area, which is about 76,000 square meter, which is roughly about 760,000 square foot of area that we have to build. But also, our scope of work was civil and structural work, including piling at block 3 and 6, tower structure, and also facade, architecture, interior design, and also the water features that you see on the right, and also the MEP work. But when you look at this project, we have several basements, which is up to about 5 basements below grade. And many of these essential facilities are built not necessarily with the deep foundation. So monitoring the building movement over the entire sites was extremely critical to make sure that we don't cause any damage to see these special projects, especially the stadium. So there's a lot, we had to spend a huge amount of time monitoring both the lateral movement, vertical movement, and also at the same time, we have real-time monitoring system that made us aware of any kind of movement that exceeded a certain limit. Fortunately, we were able to control all of that without causing any damage to any of the essential facilities, including the MRT. Now, what you see here is the picture in the blue. The overall logistic and the planning of this project is extremely complex. What you see here is the project that's highlighted in the blue is within Samsung scope. But within our boundary, we also had a retail contractor that we had to coordinate with, that had to build the mall. But also on all the infrastructure that we have around the entire site is done by a third contractor, which is Ahmad Abdelrazaq, which both in the green and the purple, or the color there. So having all this complex coordination in which we have to coordinate with everybody to make sure that everybody working efficiently. On top of that, we need also to respect how we monitoring, as mentioned earlier, the building movement over the entire site, which was extremely complex. This is what the project looked like in October 2021. We were working through pandemic and COVID-19 and movement control and so on and so forth. So it was a very challenging. What you see in the middle is the platform where we used to lift up the funnel part of the pinnacle. This is in December. We started, we raised pretty much the spire to its final height. And this is where the building as it stands today. Now, going back, again, this project was given to an architect, FKA, and Carl Fender had probably talked about a little bit more detail than me. They proposed many different options for this project with different shapes. But because of its location, the client selected the diamond shape. And the diamond shape, as you can see here, is pretty challenging from a structural standpoint, which I will speak about a little bit more as we speak. So one of the things that that we have, as I mentioned earlier, the main use of the building is an office building from level 8 to level 112. From 113 to 116, we have mostly the hotel with a 250 roughly units, including hotel and suites. And then above that, we have the amenities and the observation deck and so on and so forth. And the pinnacle in itself starts from the top of the roof at 518 and topped out at 678.9. This is what the typical office plan look like. Pretty efficient, standard office plan. And as you can see, we have about 8 mega column that will link to the core, which I'll speak about later. And with the typical hotel, again, is pretty logical in terms of the efficiency standpoint. And we have several sky lobbies at each of the mechanical levels. And again, this is what they look like. One of the challenging things that we found as we go into the project, the reason I'm talking about a little bit on the design is the wind engineering management. This project is interesting when this is done by Lera, when they make a comparison between an Arab, when they made a comparison between the wind load, as you can see, the basic wind speed in Malaysia is about only 35 meters per second. However, if you look at Shanghai, Seoul, Busan, the wind speed is much, much higher than that. But if you look at the overturning moment at the base of the building, well, it's as big as Busan, you know, which is one of the reasons, because the building shape, especially for the crosswind response in the weak axis of the building, it's very, very huge. So it made it very difficult to control the deflection. And as you can see here from this shape, also the core, even though it's long in the long direction, but from the neutral axis, there's a lot of material that didn't have a lot of effect on resisting the lateral loads. So it was very much dependent on these, what I call the mega column in the east-west direction. And the north-south, the core was big enough, but it didn't need a whole lot of help, but also was very challenging from structural planning standpoint. To understand it a little bit more, if you look at, again, is the frequency, the resonance frequency of this project, looking at stool number, the wind velocity, and width of the building. As you can see, a square, the stool number is about 0.12. But when you look at this kind of a shape, the stool number for this one is between 0.16 to 0.19, which put the building really active. It's like an airfoil. So it created a lot of challenges in terms of the structural design perspective standpoint. But worse than that, also the dominant wind was on the north-south and south directions, which is also the worst direction, the orientation from the building standpoint. Now, in terms of the wind forces, definitely control the design. And again, with the seismic, did not control the overall behavior as you would expect, but they were studied especially for earthquake, which did not have, which is in Indonesia in particular, it didn't have enough energy to really get the building moving. And we have installed accelerometers at the base of the building to monitor any seismic activities on the site during construction. Again, the building, as you can see, these are just typical wind engineering that was done on the project, including everything, cladding, force balance, aeroelastic, so on and so forth. But the building acceleration is within acceptable range. Now, what are the challenges that we have on this project? Again, as I mentioned earlier, this project is really very eventful. It has a lot of things going on with it, which makes the construction itself is very challenging. The raft, just as an overview, the building is founded on 138 port piles that founded on a 4-meter raft with the stiffening fin walls, 8 of them that connect the core wall to the mega column directly. We have 8 mega columns. They are pretty big, which I'll speak about. It's more than 4 meter by 3.7 meter. But one of the features that we have, because on the east-west direction, the weak axis, we needed to really put as much material as much as possible to control the wind drift. Some of these hammerheads, which I would call right here at the perimeter, at the tip of the core, They were 7.4 meter by 4.3 meter. They're absolutely huge element. And the core wall thickness was about 550 to 7 at 1.7 meter. But also we have 3 outrigger levels in both east-west and north-south directions. As you can see here, there are 3 stories steel trusses. And also the spire is roughly about 160 meter high, and it weighs about 1,000 ton when we needed to lift. But also the belt trusses. The belt trusses, we had about 6 of them. Separated almost at almost 17 floors. And these belt trusses transferred all the intermediate steel columns that I will speak about, which are created and have to be followed a certain construction sequence. So essentially what you hear, the summary of the structural system, looking at the core wall, initial design was C8 using C85 concrete to up to C60. And then for the mega column, C85 to C60. And in order to control the drift of the building, there were a lot of rebar were added to the project to increase the stiffness, especially in some of the critical element of the mega column that almost went to about more than 4%, which almost like more than 2,000 D40 rebar, which makes from a speed standpoint made a little bit difficult to manage. So what we propose to the client to use higher stiffness or higher strength concrete, C95, for all the mega column from bottom to the top, in which we were able to increase the strength, but also most importantly, increase the stiffness, which I will speak a little bit more about later. The same thing with the core. Especially in the weak axis, some of the elements were not very effective because of the shape. So we were able to shave the thickness a little bit by reducing the weight by about 15% of the core. But that also added, because of reducing thickness, about around 2,500 square meter of lettable space area. So the orientation of the trusses, the first outrigger is at 40 to 43. The second 75 to 78, and the third from 113 to 116. And the arrangement, what you see in the plan, in the east-west direction, we have this bifurcation of the outrigger to the mega column, and the same thing at the edge in the north-south direction. Because of these corners details, it made it very difficult to work out the connectivity of some of those. This was very challenging. But anyway, and then we have a belt trusses. As you can see in the middle here, we have 2 steel columns. They are really for gravity only. They are not part of the lateral system, and they transfer every 17 floors or so to the belt trusses. This is an overall view in terms of the construction methodology. We created the center core, which about almost 12 floors ahead of the structural steel, and sometimes even more than that. What we have is the mega column that you see here in gray. But in the middle, you have 2 intermediate steel columns that are only really for gravity, that has to transfer every 17 floor to the belt trusses. So this is the overall arrangement of the system. In terms of the floor framing, we have composite floor framing spanning between the core and the exterior of the column. This is just some of the sketches in order to understand the building a little bit more. You know, I think you can see that the building shape, you know, changed a lot, and we have a lot ongoing with that. And as you can see, also the east-west sections where the location of the outrigger, they're pretty short, they're pretty effective, very stiff. In the north-south direction, also very short, but you know, because of the core was very stiff, we didn't need a lot of to add a lot of connectivity there. This is just an overall representation of the lateral system. And when unfolding the exterior of the facade of the building, you can see that the shape changes all the time. And one thing I didn't mention earlier, but when you first look at this building, you think probably from a wind engineering standpoint, it's going to really perform very well. But actually, because of the indentation or the change is very small and we have a very sharp corner, the vortex shedding, we're not able to control that because of the shape. The shape was not very helpful in controlling that. But anyway, this one here, what you see is the green element at the outside, which represent the mega column. And they are what I would call reinforced concrete mostly. And then we have the intermediate steel column in the middle. They are in red. All the red elements are structural steel elements. This is what the outrigger look like. They are pretty massive elements. We were able to simplify the design by having a single plate rather than multiple plates here. And as you can see here, this is a sketch we developed initially. We had the connection at the hammerhead, which is absolutely huge. It was supposed to be a casting, but we really had a hard time finding a contractor who can do that. Finally, we worked with Lera and Arab to change that into built-up sections. This is just indicating the alternative detail, and that has described all the major elements. And as you can see, these members from the scale of things is absolutely huge. Some of these diagonals is about 2.2 meter by about, they're pretty deep. And this is to the scale of things, this is a person here. And the width is it's varying much less than that. And this is in the north-south directions. Again, one of the things that are complex about this is because these very high forces coming at the corner where we have an opening. So we had to resolve all the forces internally within the core, which made the detailing a little bit complex. The other thing is constructing of the mega column was also another challenge. As you can see here, we needed to speed up the work. So what we developed is a prefabricated pre-assembly system in which what you see in the sketch, erection steel column, they are pretty small. And then we created a what I call a modular system at the site, in which we pre-assembled using templates, the steel, the rebar, the ties, the connections, everything in this element is pre-assembled on site. And some of these mega column weight as much as 38 tons. And essentially we were able to use them as and erect them as a structural steel members without having to put the rebar one by one. So we were able to successfully do that on this project. Some of these mega columns, as you can see, TC2, TC3, TC7, and TC6, they are pretty big element. They are up to 3.2 meter by 4 meter. They're pretty big. And then also for TC1 and TC4 on the north-south directions, there's also big, about 3.2, 3.635 meter. So to the scale of thing, if you look at the picture on the right, you can see we have erected using a modular system for the mega column in which we pre-assembled everything and erect them like we erect the structural steel members. And we were able to create a multiple level of work. As you can see at the lowest level of the mega column, we have concrete workers are finished the concreting. The next one is assembling the second phase of the truss. And at the same time, we have all the connection of the structural steel member done without compromising the schedule. The other complexity that we have, these hammerheads, they are pretty big. And as I mentioned, they are 4.4 meter, and most of the vertical rebar at the perimeter. So to install these very long ties was also a challenge by itself. So just we decided at one point that probably as in the future, when we come down to these elements, I believe having a simpler kind of detailing, maybe it is something can be considered in the future. We tried to do that, but unfortunately we're not able to get it through because of time and some concerns that the engineers had. But we did a very detailed construction sequence, or actually ANSYS 3D, and using a detailed analysis to look at the behavior of the original plan of the, again, these hammerheads, as I mentioned, 7.6 meter by 4.4 meter. And we try to have a continuity of the web and having these divided, instead of having a single core, divided into two cores. And we did a lot of interesting study in collaboration with Seoul National University, look at the structural analysis and the behavior of these systems with different kind of, I missed maybe different kind of detailing. Essentially having these ties that ties all of the element, it makes the whole thing, the entire core, instead of having this huge core to push, to restrain, we have a much smaller one to deal with. And so we did run a very detailed ANSYS 3D, and also to look at the behavior of these systems. Essentially, there was really no major difference between the two systems. And as you can see from a single core element to a double core element, and but the strain in both the ties and the horizontal ties was more or less the same, and in fact is a little bit better than having these long ties that we dealt with. At the end of the day, we have model 1 and model 2 just to improve and to minimize the tie onto the elements. So what you have here is when we did the ultimate load at ultimate stage, there was no significant difference between the original design and the alternative model that we had. So it was in the future, I think it is something to look at. But one of the things I want to speak about is the challenges that we have also is in terms of concrete technology. As I mentioned earlier, in KL, in particular, they are the first one to use C80 concrete and for Petronas Tower, and they did a very, very fantastic program to ensure the quality control. So when we introduced the first time, and that from 1993 to 2012, there was really no significant improvement for C80. So when we introduced the C105, many people had a lot of questions, but both Arab and Lera were supportive if we can deliver that. So we were able to show that we were able to do it, and we dedicated a concrete batch plant fully on site, dedicated to produce the high strength, high stiffness concrete. So they requires, we did a lot of work, including trying mixes for all the concrete grade, mechanical properties, both cylinder and a cube. Again, a cube actually should avoid to use for high strength concrete because they are not really reliable. We cannot get a lot of reliable data. So early on, we agreed with the Arab to use cylinder instead of using a cube. And we did a lot of durability tests, creep and shrinkage test, pump simulation test to make sure we pump the concrete without any hiccup. But we also have a challenge of these big, massive elements, both in the hammerhead and the mega column, where we had to control the temperature to make sure that we don't have any kind of issues in terms of the heat of hydration. So we also did the design, mixed design for high strength. We needed to satisfy, these are the criteria that we set together in developing the mixed design, the compressive strength, mass concrete for low heat of hydration using high volume fly ash, achieving 3-day early strength, 3-day cycle, looking at pumpability with a high flow, but also testing application in which we had to look at the creep and the shrinkage in order, because as you will be talking later, the building has dissimilar material, the core moving in one, the mega column another, the intermediate steel column a third. So in order to measure the levelness of the floor and in order to keep a track of the building levelness, we had to do a very detailed construction sequence analysis. And the only way we can do it is to have an early prediction in terms of the behavior of the concrete, in terms of creep, shrinkage, pump simulation, pull-out tests, so on and so forth. So we did a pump simulation on site, near the site, some area near the site in which we did up to a 560 meter to look at the characteristics of the concrete before and after. Curing methods, also for the mega elements in terms of protection to prevent cracking. We have to have proper curing to control the thermal cracks, but also vertical and horizontal curing for everything, including the podium. Hot weather concreting, Malaysia is a hot climate. So how do we control the temperature and the mix design? Fortunately, we have a patch plant on site, and we have icing, and we also use ice shaving in order to control the temperature for the mix. And also we had a very stiff, very quality control program in order to make sure that we don't run into any kind of problem. So we have put a quality control program in terms of the raw material, concrete strength, and patching variation, and so on and so forth. So this one, what the mix design for this particular one, we didn't really use a lot of cement. We mostly use GGPS, silica fume, about 10%, 55% GGPS and silica. With the cement, we have only about 45%. And again, with that, we add a lot of additives, and we were able to control the temperature. And we did it. These are the different concrete mix design, C95. We call it C95 actually for cylinder, but actually C105 mix. Early on, we decided to the client, okay, the strength is not so critical. Okay, we use C105. We design everything using C95, which is a cylinder. And then we had a 15 MPa margin, which is pretty generous. So we designed the concrete strength to achieve 110 MPa. And we used it for only C95M and C95 high. The aggregate type is more or less the same, but we just we used a little bit more binder as we want higher and higher. GGPS increased, and the silica fume remained the same in order to keep the mix intact and to keep the flow. We did a lot of testing in terms of C105, which is very interesting, as you can see here. Initially, we decided on C95, but actually we achieved up to 120 MPa. And in terms of for all the concrete mixes, and we also looked at the E-modulus. Our agreement was to go with 40.5 at 28 days and 45, but we were able to achieve up to about 50, close to 50 really gigapascal, which is an added strength that we had. Again, we did full-scale mock-ups to look at the temperature differential between these massive elements. And we were able to keep it below the 80 degree. And because we didn't use a lot of cement, a lot of GGPS and microsilica, we didn't have the problem that we have in the old days using a lot of cement. And we also looked at the workability, in which we had initial set 590 to about 620 for the flow, and it was pretty very, very robust mix design. Even after 2 hours, we were able to achieve a high flow without reduction. But again, as time goes on, as you can see, the temperature went from 22 to 26 degrees because of the hydration process. The durability test, all of them, water permeability, initial surface absorption, water absorption of the concrete, the chloride, rapid chloride permeability test, and so on and so forth. We didn't have any of these issues. We exceeded the requirement that the project has. For the cube strength, we achieved up to about 120 MPa 115 and modulus up to about 49.8, which is about 50 gigapascal. And it just showed the pumping of the arrangement for the different mix design and for pipe length for 560, 369, and 113. So we tested all the concrete that we proposed for this project, including the C80 and C85 that you used. This is just an indication. We also what the arrangement of the pump, the pipes, and also all of that in there. One of the things that we have done from initial of the project, we have initiated a very detailed creep and shrinkage testing, very detailed program according to the STM standard for all the concrete mixes, which we needed to use for for our column shortening and construction sequence analysis that I will speak about a little bit later. So these are all tests done at Samsung Laboratory for sealed and unsealed samples, and we had everything real-time monitoring, in which we always had an access to the temperature of the laboratory in terms of how strain is happening, just to make sure there is no significant variation in the room. So everything was connected to my mobile phone. So I had almost and the team full access, including the consultant access to the this test. In terms of the structural design, after doing all of this, the question why we did all of that, as I mentioned earlier, one of the things is we needed to give the assurance to the client and to the consultants that what we are proposing is a viable option. We did a lot of that. And the idea is when we introduced the high stiffness, high strength, we did not compromise the building performance. In other words, we tried our best to keep the building deflection, deformation, elastic shortening. Even we improved it as we redesigned the whole building using high performance concrete. Almost, I would say, we had exactly the same behavior of the building to the conforming design. This is what she showed here, is the wind load inner story drift. This is deflection of the building due to wind forces. For both the original design and alternative, they are exactly the same. And the same thing for wind loads, we did the test again because there was some slight modification. The building height increased. Actually, when we got the contract, we added a few floors in which some of the wind forces increased a little bit. But more or less, the building behavior exactly the same in terms of wind forces, shear forces, everything. It was almost a perfect match. The only difference by adding high strength concrete, we're able to reduce the rebar as much as about 14,000 tons of rebar, and also we reduced the steel by about 10,000, roughly about 10,000 tons. The other thing we have to be careful with is related to the, when we do construction sequence analysis, is the soil structure interaction in terms of the stiffness of the tile and the soil itself. These parameters were given to us by Arab. So when we ran the analysis, as you can see, the building drift was H/450 in the east-west direction, but in the north-south direction, the core was pretty big. So the drift was only about 600 millimeter, which is H/850. And the alternative design almost we matched that. The only difference in the alternative design, we didn't add the outrigger in the north-south direction, the second one. We only had the bottom one and the top one. And as you can see here, did not have a significant difference in terms of the building formation. It was always within the international standard. Inner story drift, we also matched. And the building period was about 11.8 seconds in first mode, and 10.8 seconds second mode, and the torsion 3.4. The alternative, we have almost matched that. And the north-south direction was a little bit longer, but it didn't really matter what, because it was not the dominant one. The torsion was almost the same also. Since we reduced the weight of the building, of the core a little bit, so the load on the pile was slightly reduced. And we did a very detailed construction sequence analysis of the building. For each one, it took like 4 days because of the amount of data that we had to put in. And in it, we included everything because we needed to calibrate the actual foundation stiffness. We need to calibrate the actual stiffness that we got from the laboratory related to the concrete. And then as we ran through the analysis, always we wondered which model code do we use, which one is the closest. Since we did a lot of testing, what we realized that Eurocode was the best one that really, once you get the test, that can come close to what we wanted to do in order to simulate the construction sequence of the project and to deal with the differential shortening between these major elements. These are all the model codes. We took a look at it, and what we found out that probably Eurocode with the test that we have was the best. And using these creep and shrink is always challenging for a designer, which code is best to use. And once you do the test, then as you can see, there's a huge wide variation which code you use. It's really make it sometimes a little bit confusing, but as long as it is consistent, at least you have the error is consistent. So more or less, I think that's the key to the point. But using Eurocode with the test that we have was the best and that we thought. The other one is we monitored the building foundation settlement very, very closely. And what we realized, the actual site condition was much better than the originally planned. The original pile spring stiffness that was given to us by Arab was around 250 to 550. But what we realized, it was much stiffer than that. It's about 800 kilonewton per meter, which is about 0.8 giganewton per meter for all piles. And also the actual soil stiffness was bigger than what original plan. We just trying to calibrate that in order to predict the building settlement and also the building column shortening. Now, when we included everything, what we realized at the end of the day was the building deflection reduced from 1.1 meter to 900. Now it's h over 570. And then also in the north-south direction, the building deflection also reduced to 567. And then for notional load, or what I would call this a seismic, we also much better than original plan. The building period reduced from 11.9 second to 10 second, and the torsion has also got a little bit, because we reduced the thickness of the core a little bit, it was also reduced, but the stiffness was high. But anyway, at the end of the day, we also had the construction sequence, as I mentioned, between the mega column and the intermediate steel. These elements have to be disconnected during construction and connected at only the final stage. So they cannot transfer the load, as you can see from these, from floor to floor. So we also simulated that construction sequence. But the differential between this mega column and the steel column was very important, because the differential shortening between them and also the levelness of the floor is very important. So we have to factor all of that into the construction sequence to make sure that we deliver a building that is leveled. This is when we also looked at modified the foundation stiffness. We were able to calibrate the actual building stiffness early on. Since the foundation stiffness, the differential shortening, the differential settlement is also very important. So we factored that into the analysis. And as you can see, the maximum settlement that we see so far in the building is only about 40 millimeter. And our prediction was about 44. So we're very, very close together. The other thing is because of the asymmetry of the building, because of the spire and the core, the building drifted also laterally. So this is another challenge in terms of the verticality of the building. So we had a very extensive monitoring program to measure the building using tilt meters, GPS, optical survey, to look at all the building movement during construction. And because initially we expected about 280 millimeter, but because of reduction in weight and also increase in stiffness, and also we balanced the stress level between the elements, the vertical elements, especially the mega column, we're able to reduce that to about close to about 200 millimeter. And as you can see here, we've been monitoring the building lateral displacement for a long time, and it's so far as it's about 200 millimeter. And the other reason why this building drift, because the core on the south part essentially goes back, and that created asymmetry in terms of the stiffness of the core that resulted in that kind of additional displacement. As you can see, we also balanced during the design process and using the construction sequence in order to avoid a lot of complexity in terms of levelness, in terms of verticality. We equalized the stress level between the mega column and the core. And as you can see here, the maximum vertical displacement of the core and both at the edges and the hammerheads about 350 millimeter, subsequent to the installation of the floor at 30 years. And also the mega column were pretty close, other than MC1, which is very close to the spire and where the symmetry affected it, has a higher stress level. But more or less, I would say the maximum displacement in all the mega column, as you can see, is roughly about 350 millimeter. So pretty much we have a really, really balanced system through the design process in which we were able to control the metal movement and also the displacement. So part of the construction sequence, as you can see here, the vertical lines are where the mega columns are, and the intermediate steel columns, very large variability, how to control that leveled floor. We spend a lot of time into that. So we looked at different levels. We pretty much balanced it pretty well, but we did have to make a correction program in which we built all the floors about 3 millimeter taller for all the elements. For the mega columns in the north direction, we increased that to about 4 millimeter because they were displacing more. But also all the structural steel column, we made them about 3 millimeter, 2 to 3 millimeter longer, but that was done all in the shop. And we were able to balance the differential between the mega column and the steel column. It was really like a Swiss watch. I tell you, I just to make sure that we don't run into this problem or levelness issues. We spend a lot of time to make sure that is achieved, but also that has a major impact on the facade, because the facade was built within plus or minus 25 millimeter for stack joint. And if we had any kind of differential that exceeded that, that will also create another problem. So we're able to manage all of that very carefully, and the maximum displacement that we have between the mega column and the interior steel column is roughly about 5 millimeter at max. And with that, we installed a very dynamic, very detailed monitoring program for the entire building, including accelerometer at the base to measure any seismic events. We also have tilt meters at all the mechanical levels and every about 17 floors or so. We also have a dynamic strain gauges in the outrigger to measure the load distribution for gravity load. But most importantly, it gives us an idea of what the stress and strain level in these elements for wind loads. And that gives us a feedback in terms of the building behavior. And we also had GGPS and accelerometers we added at all the mechanical levels to measure the building acceleration for both wind and seismic event. But also we have very extensive survey program using optical survey to look at the differential shortening to make sure we are not exceeding those. So, and also for the power raft foundations, we also have a settlement marks and strain gauges on some of the piles to measure the actual load distribution. So it was a pretty, technically it's a pretty complicated project, as I mentioned, not only in the load transfer, the differential shortening. So from a construction standpoint, we have a huge amount of challenges. It was very, very eventful project in every way I could think of. This is just here, maybe you have seen some of these slides from Fender Castellides in terms of the project, and this is the landscape and the promenade that more or less form the main entrance, and it's open to the public. The kids can come and play because there are a lot of fountains here next to the Merdeka Stadium. This is what it may look like during you know, a normal day. And has a lot of water that is very comfortable, that's cascading from the main entrance all the way down. Again, utilization of high strength, high stiffness concrete that continue to be very important, and the utilization of super tall building in particular. We use the same thing for Calatrava Tower here. And so at this moment, this is just an images showing the pile testing program that was done before Samsung reached. When we got the site, essentially all the piles were installed. So is the D-wall. That was also a very eventful thing happened there. But here what we have is the overall site when we took it over. The overall logistic and the planning of this project is extremely critical. This is what you see here is Merdeka Stadium, and we have 7 basements next to it. And then we have Nagara Stadium to this to the south. And then also we have to be careful in a shallow foundation. And then we have the MRT stations here. And then over there we have another stadium. And all of these we have deep basements. So the construction sequence of the podium using semi top-down construction was super critical to control the movement of the project. And we had to go through a very detailed analysis, very extensive monitoring program to make sure that we prevent any movement. So we added tilt meters. We also have you know, water wells to measure the water levels to make sure that we don't have any additional sediment, especially this area is very sensitive. What you see here is we have the patch plan for the project for high strength, high stiffness concrete dedicated for this project is in this area. This is the client office, and this is here is a parking garage. But the overlap of having so many things, and it was alive because constantly it's changing all the time. As you can see here, the top-down construction, we have to complete the entire floor. As you can see, we had a lot of lateral restraint to prevent any lateral movement for the happening on the Nagara Museum, Nagara Stadium, but also this stadium, Chinese stadium. I forgot the name exactly, but and this is here. One of the other things that we struggled with is related to installation of the raft. Again, in order for weather protection, we added this cover. Essentially, we have used the light fabric with a 15mm cable that spans about 40 meters to cover the entire area to be able to work without any hindrance in terms of in terms of weather or anything, because we need to cast a raft in about 48 hours. And so the construction sequence was very critical. We developed a very simple system to install this fabric. This is a hand sketch that I made of the system. It was very simple, but we installed it over a short period of time. And this overall logistic, as you can see, this is like a curtain to move in and out in case we needed to open it or close it. It was an easy thing to do. This is what the when we casted the raft, what it looked like inside, fully protected. And so um, this one just a short video to show the construction, I think, of what it looked like, during construction, where we have the stations to look at the concrete quality before it goes into the site. We have an overall logistic and the planning over the entire area. And then as you rotate around the project, the circulation, the pump, everything pumped down using pumps into to cast the raft. That's pretty much it. This just shows the construction of the project as we move, installation of the outrigger. As you can see here, this is the hammerhead area, and then a single plate that continues as part of the outrigger to take most of the shear, most of the tensile forces. Mega column installation. It's just a construction sequence. As you can see, the logistic and the planning of the project constantly change to accommodate many things. This is an overall core. The core itself was divided into 3 zones. Center zone with the hammerhead, A, B, and C, and the center zone where we have the outrigger, and in the north and south we have the south and north outriggers. So we divided the core into 3 zones, especially for the outside, and then we came back to do the inside. Just a construction sequence. As you can see, the mega column is not casted with concrete, but we use the structural steel to speed up the construction a little bit with that. And with that, I think pretty much these are just construction photos, the progress photos for this project, the installation of the last belt truss and an outrigger. This is installation of the spire, final piece. And now the spire has been completely lifted to its final position in November. And that's now, this is just images of the project that we have. Just in conclusion, I'd like to just to play a short video. Some of the facts of the project. It's 118 floors. It's the tallest building in East Southeast Asia, surrounded by critical sites. And the building is expected to be completed end of 2022. And with that, I end my presentation. I know there's a lot of material to cover, especially from a technical standpoint. But again, as I mentioned, this is really was very challenging project in every way you could think of. So at the end of the day, we struggled through COVID-19. We had a lot of challenges on and off because of Corona, and we have completed this project very safely. without any major accident, and there were no fatalities on this entire project. So we are very happy that we have completed this project successfully. And I would like to thank both Arab and Lera for all the support during this project. The client in particular was extremely supportive for us all the time, especially during pandemic. And many times we had to beg for them to allow the CDC and building official to allow us to proceed forward. So we did all the precautions that is really required to make sure that we continue to work on this project. And it was slow, but at least we were able to get somewhere by completing it, the structure, and hope to complete the project by end of 2022. Thank you so much.
Well, thank you, Ahmed. That was really an incredibly detailed look into a project that I think is awfully hard for laymen in particular, like me, to get your mind around. But certainly the takeaway for me is that I think, well, for me as the Skyscraper Museum, is we're delighted to be able to indulge our audiences, many structural engineers on the call here tonight. And there were a couple of questions, but I think since we are there, and they were on details about thermal gradients and some other rather specific questions. And since there is such a richness of detail already in your talk, I think maybe concluding with just a couple of questions in a couple of minutes, since we are kind of over our normal time. I wonder if you could reflect on the percentage of the process that you described to us that was preliminary to the construction, and then the role during the actual construction. I was certainly very impressed with how much thinking and planning and analysis and monitoring of behavior in theory that you applied even before any construction was underway. So can you kind of enlighten some people who have no sense of how much expertise you need to bring into a process, not reacting, but proacting?
Yeah, let me put it this way. For when we bid on the project, obviously the client and the consultant have to go through the due diligence in selecting the contractor. So we really have to fully understand the problem and the issues and how to build this building. Because otherwise, in order to factor in all the costs, we need to know all the issues that are involved in this project. And usually the bidding process is not that long. So we need to, without experience, I mean, people will not really know where to start. But with us, I think we spend a huge amount of time due diligence on the building, understanding the behavior, understanding the issues that we have to face, in terms, not necessarily to understand them fully, and also to appreciate the complexity of them and to come up with solutions. For example, one of the requirements that the client had is the contractor has to run a construction sequence analysis to understand the building settlement and behavior and movement, and make a correction program to make sure the levelness of the floor. So for us, that's through a lot of challenges on us, for example, to go ahead and understand the building, to know what we have to do. And through this due diligence process, we not only understand the behavior of the building and what needs to be done, but also give us an opportunity, an area where we can add value to the project in terms of the cost saving, in terms of time saving, in terms of additional area, for example, with this project that we added to this project. So we do need having a very experienced contractor who was able to identify and look for these issues, it become very extremely critical. So we did have to look at the construction sequence. We have to look at the schedule. We have to look at the complexity of these elements. We have to propose alternative design to make sure that we meet the client's schedule, and so on and so forth. So there's a lot of planning to be done well in advance. And also, anything we propose an alternative, we have to put the cost and time effect of it. Otherwise, no benefit to the client, right? So there's a lot of things involved. And after that, you have to, again, go through the final design and collaborate with the consultant, including like Lara and Arab, to make sure that we did not miss anything, and being able to respond to their concerns by doing the work. And it's quite involved. And as you can see, as I mentioned, the transfer, every time you create an event in a building, you create a challenge, because you have to stop, think, follow a certain process. And that is something, it happened every 17 floors, because you get the bell trusses, and all the complexity with the detailing. So there's a lot of events happening as we go through the buildings.
Because we are quite a bit over our time, I'm going to ask you one more question for a short answer, and that is, now that you've been involved in constructing some of the world's tallest buildings, and super talls as a category, what do you, is each project different enough from the other that it's a new building every time, or is there, what are the lessons learned that apply? Is there a kind of continuing professional expertise that's shared, not just resides in you and your experience, but is shared across the profession?
Well, to be honest with you, every project is different. For example, going from Burj Khalifa, it has certain characteristics. And I would say for the most part, it was an uneventful project, mainly because there is a consistency in the design and construction. We didn't have a lot of events. So practically we keep moving, just like mechanize the entire construction process, right? It was same elements, same sizes, same reinforcement, same formwork, same everything all the way up. And if any you need to, you just drop things, you don't change things. Mm-hmm. Taking 118, there's a lot of events, which means that a lot of things, a lot of planning, a lot of things we have to do well in advance to make sure that we don't run into technical issues. But the problems essentially is all the same. Almost you have to be aware of all the issues that are involved. But some of them are not that critical. Others are very, very critical. So, ultimately, the uneventful project, you have more streamlined the entire process, and you end up building it on time and without any hiccups. Others, you will run into challenges along the way, unexpected sometimes. Mm-hmm. So anyway, every project, I would say, is different, but I strongly believe integrating the design and construction for super tall is an essential part of having a successful project that deals with the issue well in advance. So when you go to the construction, it's already planned. It's already incorporated into the design, so you don't run into a lot of technical challenges. So that's why I'm very lucky, I'm very happy that being able to be involved in the design and the construction. As you design, you think about how you build it, not in one way, many 3 different ways. So then in that case, you have a better assurance in terms of what to expect in terms of quality, safety, what you get at the end of the day. And also that also related to cost and schedule, always, Yeah.
Well, thank you for expanding our minds and our vocabulary for eventful buildings. That's something that I'm going to use, I think, going forward. It really was such a pleasure to be able to partake of your expertise again on yet another building, and we'll look forward to your next one and invite you back in order to walk us through all the aspects of that project. So. Thank you, Ahmad Abdelrazaq, tonight for sharing your knowledge once again.
Thank you so much for all the attendants have attended, and I wanted to again thank you for inviting me to be part of this. And definitely your program is just amazingly fantastic. I think it's always for me, I always follow, and also I think I'd like to thank B&B. For being very supportive, and all the consultants who have been with us on this very challenging project, and we hope to finish it soon, and everybody will be happy. And at the end of the day, I think the client, most importantly, have run through a lot of challenges. Having from 2012 to 2022, that's almost a 10-year period, which is pretty long. I mean, so it does have a financial issues. But anyway, thank you so much, and thanks for everybody attending here. And I hope one day we'll go LACTA 2 and LACTA 3 is coming up. This is another challenging project in a different way. So thank you so much.
We'll see you then, and we'll everybody check back on our website, because we have launched now our winter spring series. We have a lot of book talks, and actually we're going to be looking in the spring at construction history, going back into the late 19th century in New York and Chicago. So that's our series semester coming up, and we'll be able to bracket our construction history with Merdeka, Burj, and the others in the 21st century. And now we'll look back to retrieve some of those stories in the earlier time. So onward and upward. And we'll thank you, Ahmad, and we'll see you all next time.
Thank you so much. I'm sorry for going overboard. So.
No problem.
Okay.
Take care.
Thanks a lot. Take care. Bye.
To welcome everybody to a coda on our program of Worldview, the series of 13 lectures that we did last year, beginning in January. And so here we are, alas, a year later into the COVID regime, and it seems as relevant as it ever was to be doing virtual programming. We took advantage last year of the virtual programming format in order to bring people from all over the world, indeed, as speakers. And our speaker tonight, Ahmad Abdelrazaq, is speaking for the second time, because he did such a tremendous job in closing our series of lectures last year with the talk that he gave on the project in St. Petersburg, the LACTA Center, for which he was the project manager on the construction. And we thought it was particularly important in this series on architecture and engineering supertalls to also bring in the issue of construction and constructability as part of the design process, as part of its implementation, and as Ahmad will also describe, the monitoring of supertalls, because these buildings are unprecedented in history. Each one is a unique problem that needs to be solved, but they represent a kind of growing body of knowledge. And that knowledge about supertalls and their performance is expanded by the experience of the buildings standing in the real world. So the construction of those buildings, but also understanding how they perform against the behavioral models that were established in order to allow their creation, is one of the topics that we're exploring. And tonight we get the opportunity to do that with the building, the Merdeka 118 in Kuala Lumpur, a building designed by Carl Fender of Fender Katsumitidis, in a Melbourne-based architectural firm, working in Kuala Lumpur on a design that Carl spoke about in our series for about an hour in a lecture. And all of our lectures, of course, were captured on video, and they're on our website and they're on our YouTube channel. So you can watch there Carl's 1-hour lecture on the design of Merdeka and the surrounding project complex in a really excellent lecture that in fact is the most popular one on our YouTube channel so far. It has more than 4,700 views. And I think that's a testament to the interest around the world, and especially in the Pacific Rim of super tall construction. So Ahmed is also the project leader on the Merdeka 118 project. And because the building has just structurally topped out and the spire has been added to achieve a height of 660 meters, making it the second tallest building in the world after the Burj Khalifa, which Ahmed also worked on as a project. It's a delight to be able to get this, from the horse's mouth, the story of how this building is fresh from its construction cranes and due to open next year as the building is enclosed and it's prepared for occupation. So let me introduce Ahmad Abdelrazaq, who until just recently is the executive vice president of Samsung C&T construction, and specializes in tall building projects. He has spent 18 years at Samsung after leaving SOM around 2004, when he did work on the design, development, and the construction drawings for the Burj Khalifa. And then he went on to bid on that project for its construction. So he's had an incredible career working as a structural engineer, working in construction projects, and doing all kinds of design analysis that I think he will make clear in his talk tonight, how important it is to think through the issues from a slightly different vantage of the architectural and the structural engineering and MEP engineering design process. All of these things need to come together in the